Okay, hello everyone. Today I'm very happy to introduce Dr. Markus Mosbech. Markus is someone that I met last year in a trip to Sydney, Australia, where he did his PhD. Since then, he moved to Aachen University in Germany, where he's doing his first postdoc. So Markus is a cosmologist, but he's also very well versed in particle physics. And most of his research is focused around trying to find ways of distinguishing between different particle physics models of dark matter through cosmological surveys. And so without further ado, please welcome Markus.
Thank you very much, and thank you for the invitation. Yes, as implied by Miguel, I'm going to talk about how we can use cosmology to determine the particle physics of dark matter. I don't have another introduction slide about me, but it's good that Miguel gave an introduction, so we can just get started. So in this talk, I'll start by giving a quick introduction to what kind of stuff that we're going to be talking about, then give a short presentation of this test case model that most of my work has been using, then go over gravitational waves as a novel type of constraint of dark matter particle physics, and finally cover some other supplementary constraints. All the details are in these papers if you want to look that up now or afterwards. Of course, I've not done all this myself, so I'd like to thank all of my collaborators. So we start from square one and ask ourselves, what do we know about dark matter? We know that there's quite a lot of dark matter out there in space, and it needs to have either zero or very limited particle interactions with standard model, only really talking to the world we know through gravity. We also know it clusters gravitationally, at least on relatively large scales. This is how we know it's there, because we can see its effect through gravity in galaxies, in galaxy clusters, in CMB, etc., from rotation curves and from the shape of the CMB power spectrum. Then we also know, so we know a lot about what dark matter is not, because a lot of research has gone into investigating different dark matter models, and a lot of them have been found not to work, but that doesn't really tell us what it is. So one of the questions is, what can we learn about dark matter now that we have access to a new probe, such as gravitational waves? And there's different ways of trying to learn more about dark matter. These can be broadly sort of split into two different types of approaches. So there's laboratory experiments, such as direct detection or colliders. In direct detection experiments, we set up some big or less big tank or other target where we hope some dark matter particle will come in and scatter off one of the nuclei or electrons in the experimental setup, which will deposit some amount of energy that we can detect. And then through understanding our backgrounds and our signals well, we can identify this and saying, oh, this should be a dark matter signal. And we might be slightly closer to a particle physics model of dark matter. Right now, only the Dharma experiment in Gran Sasso reports seeing a signal, but the signal is in strong tension with multiple other experiments. So there's no real conclusion on that yet. Then, of course, there's collider physics, where the idea is if we smash particles together at very high energies, then maybe we can access higher energy interactions where couplings to dark matter particles might lie. And these, and if we then see some missing energy in our detectors, in the sense that we knew how much energy the collision had, and we can see all these particles that come out, and the energy doesn't add up, then there might be some dark matter particles coming out that did not scatter in our detector, because of course they interact very weakly with the standard model, and then we might have a better idea of the couplings, and so the particle nature of the dark matter. Again, there's been no conclusive evidence. Then we have astrophysical signals, where one approach is called indirect detection. This is where we sort of look for normal photon signals from annihilation or decay of dark matter. So if dark matter annihilates or decays, then it will either possibly decay into standard model particles, which could include photons or could include electron-positron pairs, which would then annihilate into photons or similar, and this would give us gamma ray signals. And there's been a lot of work into this, looking at areas of high dark matter density, such as galactic center or globular clusters, to see if we can associate gamma ray signals from this region with annihilation or decay of dark matter. Again, nothing has been conclusively decided. Many of these types of signals could, for instance, also be associated with unresolved pulsars. And finally, which is most of what I've been working on, is structure formation constraints, or structure formation information, where we look at the way structure forms over the history of the universe, and from that we can infer properties about our dark matter particles, because the dark matter particles are essentially the drivers of structure formation. The dark matter can collapse before baryons are decoupled from the photons, and therefore form the seeds of galaxies and galaxy clusters. And we can therefore check if what our model predicts match what we observe in our universe. So as I alluded to, the universe begins in a very homogeneous state after inflation, is our idea at least. And at these times, baryons, so that in this case means protons and electrons, this very cosmological description, where because the energy is quite high, the temperature is high, there are no neutral atoms yet, meaning that the universe is very opaque, and there's around 10 to the 10 photons per baryon. So these will scatter all the time and essentially behave as one coupled fluid, where the photons provide pressure that will just make sort of a pressure wave in the baryon photon fluid expand, and the baryons can't collapse under gravity, but instead will oscillate. And this is what's called the baryon acoustic oscillations. If we look at the growth or evolution of perturbation on a given scale, here 1 inverse megaparsec, we can see that the photons and baryons follow each other very closely, begin to oscillate when the scale enters the horizon, until we have some decoupling around the time of CMB is emitted, and the photons will just free stream, and the baryons will start collapsing and forming structure. But meanwhile, while the baryons have been busy oscillating, the dark matter has already started forming structure, and this sort of already exists, so the baryons are just catching up and falling into the potential wells already created by the dark matter. And so one way we often try to probe these dark matter models is looking at models with suppressed structure formation. So what if something happens that prevents our dark matter from collapsing and forming structures? Because, well, this is the thing we know dark matter does, at least on large scales, is collapse and form structures. So this is a nice little knob to turn to see, can we find any deviations, anything we can look at in our data. So these types of models can be broadly thought of in 3 different categories. There's warm dark matter, which it's very close to the sort of cold dark matter paradigm. If we produce it thermally, so it's just coupled to the dark matter particles early on, and it has a relatively low mass on the order of a few keV, then then it will have a higher thermal velocity than if it was MeV or GeV, TeV scale, meaning that it will free stream a certain amount, similar to what we see neutrinos do. And this free streaming scale is set by the mass if they were just looking at normal thermal production. And it turns out that keV scale has a free streaming length that is sort of broadly probable by things like dwarf galaxies and so on, in the sense that if we see dark matter structures forming at some small scales, then this scale free streaming length has to be smaller than this scale, otherwise these objects couldn't form. And then we have ultralight dark matter, which has wave-like behavior on astrophysical, maybe even cosmological scales, because of their very low mass, because suddenly their de Broglie wavelengths becomes on the same scale as these astrophysical objects like dwarf galaxies. And again, we know that which means that there's not really any structure smaller than these scales, because our particles are actually of this scale. Then finally, we have interacting dark matter, where if you have a dark matter particle that interacts with a light species in the standard model, or possible dark radiation component, then small scale structure will be suppressed due to scattering. This is what's called collision damping, and it's essentially the same thing we saw in the baryons, is that if there is a coupling between a light species such as photons and a heavy species such as baryons, they will undergo oscillations and be unable to gravitationally collapse until they decouple. And if the dark matter was interacting with some light species, could be photons, could be neutrinos, could be dark radiation, then we would see the same thing. And the time of decoupling sets the scale where this structure is suppressed and where we would see these oscillations. So my work has generally been focused on dark matter neutrino scattering in particular. So this is a nice baseline model, because we don't really have to worry about the knock-on effects on baryon and photon physics, because the neutrinos are so weakly coupled to the rest of the standard model anyway, that any new physics we put in between the dark matter and the neutrinos isn't going to affect the physics between photons and baryons, etc. Unlike a model with, for instance, dark matter baryon scattering, where you have to worry about what happens to the baryon temperature if it can dump energy into the dark matter reservoir, or what happens at late times when you have both high dark matter and baryon densities in the centers of galaxies. There's also nice particle physics motivations because neutrino physics has remaining open questions. For instance, how do neutrinos get mass, which in principle could be connected to a particle physics model for dark matter. And for simplicity, we're only covering velocity-independent scattering, similar to Coulomb scattering or Thomson scattering. So in the early universe, the evolution of these density perturbations, so that's the deviation from the mean density, can be evolved using the linear Boltzmann equations. This, to some extent, also holds at late times on large scales. It pretty much holds whenever the perturbations are small. And this is really good for CMB predictions, because the CMB was emitted at a redshift of around 1,000, 1,100-ish, when these perturbations were still very small. And as we saw in the plot earlier, then the photon perturbations have remained pretty much unchanged. They haven't been growing, just free streaming. So they're still small. This is also what we observe in the CMB, that the anisotropies are on the order of millikelvin or microkelvin compared to the actual mean temperature, which is in Kelvin. And additionally, these linear equations can be used to produce the initial conditions used in nonlinear simulations of structure formation, which are necessary to produce these nonlinear observables that we're interested in at late times. So I'm not going to spend a lot of time on these slides. These are just the evolution equations for our dark matter neutrino interaction model. What you see in black are the normal non-interaction equations, and all the stuff in blue are sort of the extra terms that come from the interactions. So essentially, we get a term in our dark matter equations that looks just like photon baryon scattering, but with neutrinos and dark matter instead. And we get sort of a velocity-dependent term or momentum-dependent term for the neutrinos, because we can't describe them in the, because we have to treat them momentum bin by bin when we are looking at the massive neutrino case. These are just a lot of big equations. I can explain them later in detail if anyone is interested. Otherwise, you can just accept them. So, as I mentioned, there are three broad categories of models that all lead to a suppressed matter power spectrum. And while this is true, they have some subtle differences. We can see here three different types of model with and each model we are looking at three sort of sets of parameters, where leading to different suppression scales, where you can see the dashed lines are warm dark matter, the solid lines are interacting dark matter, and the dotted lines are these type of ultralight dark matter models. And we can choose parameters so we get essentially the same suppression scale, even if the shape of suppression is not exactly the same. The most striking feature is perhaps that the interacting model will have these strong oscillation peaks due to these early dark acoustic oscillations that I mentioned. So another reason that this particular model is interesting is that now two different groups have been looking at it, other than me, and both have found that there might be hints in the data of a preference for a non-zero interaction strength. Back in 2021, this was done by Diana Hooper and Matteo Luca in Brussels, where they looked at Lyman alpha data. And more recently, this was done by Giare and others who looked at new CMB data from the South Pole Telescope and ACT. And they also found a preference for a non-zero value, though interestingly not the same non-zero value as the previous study. But it's always good when you have some interesting signals. So how can we use this suppressed structure to get any predictions about gravitational waves? And conversely, how can we use gravitational waves to learn about suppressed structure? Essentially, if we suppress our structure on small intermediate scales, we get less or delayed galaxy or galaxy progenitor formation. And if we get fewer galaxies or the galaxies form later, that in turn means we get less star formation or delayed star formation. And again, this would mean we get fewer black hole binaries or delayed formation of black hole binaries that in the astrophysical case comes from the end of life of massive binary stars. And if we form fewer of these or they form later, then we will end up detecting fewer of them in our detectors. So in terms of the work we did, we have our input parameter for a dark matter model, which is this parameterized interaction strength U. We then use this to compute our linear matter power spectrum, which we can feed into Gadget, the n-body code, and predict a halo mass function. We can then similarly run our galaxy evolution history code egal form and cross-check that the halo mass function matches the one we get from Gadget to compute our star formation rate density and the metallicity distribution. And then we can feed this into the the binary merger population code COMPASS, which will give us the binary black hole merger rate history over cosmic time. So simulating suppressed structure has some caveats in the case of this type of model with suppressed small scale structure. Namely, if we're looking at the halo mass function, if you use a normal n-body method, you get these types of spurious low mass halos that occur due to fragmentation in the dark matter particles, namely because it's essentially a discreteness effect, because the dark matter density is modeled by discrete particles rather than a smooth field. You can get these halos that should not exist, especially in low density environments. and that gives sort of an upturn at low masses. And you can see, running the same cosmology in different box sizes, this unphysical upturn can be pushed to smaller scales. But again, it means we can't necessarily know which of the halos down here are real and which are not without doing a very cumbersome analysis. So one way of getting around this is using an analytical halo mass function rather than just taking our halos directly from the simulation. Just feeding our linear matter power spectrum directly into a Sheff-Tolman halo mass function does not accurately capture the level of suppression. So you can see here for the 3 different interaction strengths we've been looking at, what Sheff-Tolman thinks should be the halo mass function and what it actually is in the simulation cutoff, where we start to think it's less physical. And we can see that, especially for the larger interaction strengths, these do not match well. So we have introduced this additional, rather than using the Sheff-Tolman on the linear matter power spectrum of the interaction model, we can compute it from a non-interacting matter power spectrum and then use these fitting parameters that can tell us about that can then be used to very accurately predict what the suppressed halo mass function is, where this beta parameter that this means that M beta is the mass associated with the scale where the power spectrum is suppressed by 10% relative to lambda CDM, so non-interactive case, and then alpha is the best fit power for this. And yeah, as we can see, this fits our simulation data extraordinarily well. So you can then use this to generate our galaxy populations, because rather than use the direct halo merger trees from our simulations, because we have these spurious halos, we can run GalForm in a Monte Carlo method, where you, from the distribution of halos today, it can generate merger trees back in time using an extended projector method. So essentially what happens is we have our galaxy today, and the code then thinks, okay, this could be caused by a merger of 2 progenitors, which in turn could be each caused by mergers of progenitors, etc., etc. And using semi-analytical models of galaxy formation, when these merger trees have been generated, it runs galaxy evolution back forwards in time and gives us what's the star formation rate, what's the metallicity evolution, and so on of our galaxy populations at different times in the universe history. And then the resolution of this is set by the smallest progenitors we track. So we can say, okay, this halo is so small that we're not really interested in what came before that. So at a first glance, we can also use this to actually look at what is our model's impact on galaxy populations before we even get to gravitational waves. And what we find is that these 10 to the minus 7 and 10 to the minus 8 interaction strength models can well describe the current galaxy luminosity function, while these 10 to the minus 6 models are unable to capture the current galaxy population, even if we completely turn off supernova feedback, which is the main effect that suppresses galaxy populations, and thus is maybe the most degenerate with the model suppressing structures. What we find is that we overpredict the very luminous galaxies, and we still can't produce the low luminosity galaxies, meaning that we can essentially rule out the interaction strength 10 to the minus 6 just from looking at the galaxies. And yeah, this actually rules out both the Lyman alpha preferred value and the hint seen in CMB. And yeah, because we can never reproduce this, this is a fairly robust constraint. Then to generate our compact binary population, we take our star formation rate density and metallicity evolution we've obtained from our galaxy modeling and feed this into the code compass. And it's essentially what we find is that the rate where we generate binary black holes depends on the interaction strength as we expected, where models with stronger interactions have more suppressed rate of formation. And essentially what we can see is that the merger rate in solid lines is at a delayed tracer of the formation rate of the binary black holes. So which in turn is essentially a trait. So while the formation rate is a tracer of star formation, because when you have star formation, you get these heavy stars that only live for a short time and end their lives as black holes. And there is some dependence on the metallicity in terms of how likely are these stars to end their lives as binary black holes rather than leaving no remnant or having too much wind, so they have so much mass loss they become neutron stars, or they sort of rip the system apart, etc. And this is captured by drawing from these stellar tracks computed with the code MESA. That's what COMPASS consists of. And then, yeah, using our input star formation rate density and average metallicity. So the question is, can we use our current gravitational wave interferometers to tell us anything about dark matter? And unfortunately, the answer right now is no, because all the models are currently consistent with the observed rate. You can see the lambda CDM, so no interactions, and the small interactions are all right here near the upper limit, while this model we've ruled out with galaxies is sort of near the middle, but all are within this allowed range. And well, what we can say is that when we look across cosmic time, we can see that these models also end up looking much more similar today than previously, And so we're limited by the fact that we only really have reliable rates from LIGO, Virgo, Cagra at very low redshift. So what about the next generation? Since the rate at early times is very strongly affected by the delayed structure formation, we could potentially use high redshift observations to constrain these models. And what we can predict is that the Einstein telescope and Cosmic Explorer will be very high, will be sensitive up to very high redshifts. They will essentially be able to see all binary black hole mergers in the universe up to the reliability of the data processing, which is fortunately not my job. So that's our analysis shows that for binary black holes with a total system mass of down to almost only 10 solar masses, then we should be able to get a signal to noise ratio up to redshift of 10 then we would have a signal to noise above 10 for pretty much any mass. And this will let us set very powerful constraints on these. So what we see here is sort of the amount of binary mergers with the best fit redshift larger than this Z star as a function of Z star. So this is after folding in the redshift uncertainty of the measurement. We see that we can clearly distinguish definitely this 10 to the -7 model from 10 to the -8 and CDM. And yeah, this 10 to the -6, which is ruled out by galaxy formation, is also extremely different. And this, again, the reason we get this stronger constraining power is because we become sensitive to the higher redshift where the real differences between the models live. So of course there is some model uncertainty in the binary formation physics. So we've performed sort of a simple Fisher analysis comparing the effects of our dark matter interactions to the different astrophysical parameters of the binary formation models. But fortunately for us, what we find is that the effects are not really degenerate. So what you see here, the solid red line is our maximum interaction strength 10 to the -7, but using the fiducial model for the astro parameters. And these different lines around 0 all correspond to setting the interaction to 0, and then each of them varies the an astro parameter to the maximum extent. And we see that sort of the shape of the change is not degenerate with our interaction strength, which all of these they generally have the largest effects. Either they are effective at all times, like this one, but even this one and pretty much all the others have the largest effect at late times, where our model has the largest effect at early times. And this is also what we found in our Fisher analysis, that our interacting dark matter model is, the effect is just not degenerate with any of the astro models. So this is promising, even though of course there is quite a lot of uncertainty in the modeling of binary black holes. So we can compare this interacting scenario to the warm dark matter scenario, and running n-body simulations of both of these leads to the conclusion that at low redshift, if we run simulations with models that have the same suppression scale as shown earlier, we could choose model parameters such as the suppression scale matched, even if at the linear level, even if the shape didn't quite match. We see that after undergoing nonlinear evolution down to redshift 5, 4, 3-ish, then the oscillations we saw in the interacting models are completely washed out, and they are essentially indistinguishable from a warm dark matter model with a given warm dark matter mass. And we find that the same actually happens for dark matter that interacts with photons. So how would we, so this is both good and bad in the sense that it means we can, if we find constraints from structure formation on one of these models, they can essentially be applied to all of them if it happens at these low redshifts. The unfortunate thing is that any constraint we find at these low redshifts or signal, if we are being optimistic, could not really help us distinguish between them. We would just know, oh, I guess we have a model with suppressed structure formation. So looking further back, we can see that we need to go to redshifts of 15, 10, 15 or higher, where if we want to still be able to observe the characteristic oscillations of interacting dark matter models compared to warm dark matter models. This would be an extreme challenge. These redshifts can, in principle, be probed with the SKAO, with the 21 centimeter line, but it's would take a deeper analysis to determine if we would actually have the sensitivity and resolution needed to detect oscillations such as these at such high redshifts, where analyses have been performed that shows us that these type of suppression at low redshifts can definitely be probed by the SKA. So once finished, and if someone takes the time to do the observations, it could potentially put constraints on interacting dark matter all the way down to 10 to the minus 8 interaction strength. So that's essentially my conclusions, that the next generation of gravitational wave observatories can be used to constrain suppressed structure and improve upon our current limits. And similarly, SKA will be able to constrain models with suppressed structure to an even greater extent. And finally, that high redshift measurements will be absolutely key to distinguishing between different models that suppress small scale power, because we find that at low redshift, they pretty much all look the same. So here is sort of an overview of the state of neutrino dark matter interaction models and the existing limits. Thank you all for your time, and happy to take any questions.
Hey, thanks a lot, Markus, for that amazing talk. It's very interesting to hear what you guys are doing. So for all of the attendants, if you have any questions, please raise your hand in the chat. And while everyone gathers their thoughts, I wanted to start with a couple of questions. The first one is probably very dumb, but I noticed that the data that you're using for a Hello function comes from 2DF, which is a survey from the 90s or whatever. Is there a reason why you're not using SDSS or something a bit more
No,
modern,
I think,
or just because, yeah?
I think it was because this was readily available and easy to use.
Okay, that's good. And so probably a bit of a more complicated question. So I saw from your black holes merger as a function of redshift curve that actually the information requires redshift measurement, right? But and I don't know nothing about gravitational waves, but I thought that gravitational waves only gave you 2D position, right? Not redshift. Or can you also get a redshift measurement from
so
that?
when you do the signal analysis of the waveform, you can sort of try and fit to this big library of functions they have, and you can try and make your best guess for the redshift. And sometimes you can even sort of, if you have an electromagnetic counterpart, that can help you even more, right?
Okay. Yeah, I'm guessing at redshift 10 or whatever, it's probably going to be very hard to have the counterpart. Yeah. But I'm guessing that it's also why you are only requiring the mergers larger than a certain amount, right? So you don't have to measure the redshift super precisely. It's just
yeah.
Okay, that makes sense. Yeah. So another question I wanted to ask a little bit about. So you mentioned that when you make your when you test your model with Lyman alpha data, the model prefers a value of interactions that was already sort of discarded by.
So I'll just to be clear,
Okay.
I didn't do this test. Someone else did the Lyman alpha test.
Okay.
And well, this was also done before we ruled this out with galaxies. But yes, go ahead if you had.
Right. So basically, so I'm guessing this preferred value comes from like an MCMC or something.
So they did an MCMC based on with using sort of a simulation based Lyman alpha likelihood where they had a sort of way of fitting the linear power spectrum to a model, to a nonlinear model, and then interpolating in sort of a grid of simulations to see what sort of Lyman alpha signal they would produce.
So do you remember if this MCMC discarded at 1 sigma non-interactions? Like,
yes, yeah, I think they found. So this is the posterior for the interaction rate, right? And I think this is either a 1 point something or a 2 point something away from zero, a sigma.
Okay. So in that case, maybe 10 to the minus 7 or whatever your current margin is still preferred by Lyman alpha over.
I think what I would say is that these are incompatible results.
Okay. Good. Okay. Good to hear. Okay. And then so the final question that I had was a bit more technical. So I noticed when you are describing your methodology, and maybe you mentioned this, but you are using both a semi-analytical model and a simulation, right? But then at the end, the model comes out of the semi-analytical model.
Yeah.
And I didn't get what was the role of the simulation in your methodology then.
So the role of the simulation ends up essentially being as a cross-check of the semi-analytical model to see that the halo mass function that the semi-analytical model uses matches the one we get from simulations up to the point where the simulation becomes unphysical.
Right. And that is because of the suppression thing that you were saying, right? That there's like this physical effect. Okay.
Yeah. So otherwise we could have used a semi-analytical model on the merger trees directly from the simulation, but because we don't really trust the very low mass halos, we would rather run the semi-analytical models completely separately and then just look at the halo mass function in that and cross-check that it matches with the simulations up to the point where it's physical.
That makes sense. And the last question for me, and then I'll let other people speak, is can you maybe explain a little bit, was it called COMPAS, the code that you use for the merger rates? Can you maybe explain a little bit how can COMPAS compute from your semi-analytical model the ratio of black holes, of black hole mergers, I mean?
Yeah, so essentially COMPAS is built from this huge library of stellar evolution tracks computed using MESA. And then it has sort of population level statistically based sort of method of saying, if you have this sort of metallicity and you have this sort of star formation rates, how many stars of each mass will generally be formed, and then when they evolved, how will they sort of at a population level end their lives, and how many of these will then become black holes and so on.
Okay. Okay, thank you. Let me check. Does someone else has another question? Yeah, I see Rodrigo. Rodrigo, please go ahead and ask your question.
Yeah, thanks for the talk. Maybe this is a bit naive, but when you show the effect on the halo mass function in this type of models, this kind of go against what JWST prefers, right?
Yes and no, in the sense that I assume you're talking about these very high mass at early time galaxies.
Yeah, exactly.
So in principle, yes, maybe, but also in practice, what you will see is that like it depends on the scale, right? You have some scale below which the halos are suppressed, while the population above that scale is generally unaffected. So if you have a suppression scale smaller than these large early galaxies, then it would not really be a problem.
I see, but in any case, it doesn't help if we take this measurement seriously.
Yeah,
I see. Thank you.
But yeah, I think we're still waiting for some more what's it called? Some more spectroscopic redshifts for these galaxies, I think, before we throw out any models.
Okay. We maybe have time for one last question if someone is around. All right, I don't see any more raised hands. So maybe we can stop the recording